Okay, so now we're live. All right. Well, I think we're live. Hold on. Okay, so we're live now. So let me get out of this here. Okay, so back to this. All right, so we can find out what M is. Okay, what's going on here? I'm sorry, folks. Having some hiccups here. Okay, so we can find out what M is by simply plugging in the values for delta TF and okay, so for delta TF would be the change in the freezing point, which is minus 6.51 degrees Celsius, minus 0.00 degrees Celsius, divided by the KF value, which is 1.86 degrees Celsius over M. And according to my calculations, that would be equal to 6.51 divided by 1.86. So according to my calculation, this works out to be equal to 3.50 M, not degrees, I'm sorry, M. All right. So that's the molality of the solution. Now, remember, the question is asking for the boiling point of the solution. So in order for us to calculate the boiling point, we need to find delta TB of the solution. Delta TB of the solution will be equal to KB times M, which would be 0.512 degrees Celsius over M times 3.50 M. And we work that out. So that would give 3.50 times 0.512. And according to my calculation, this works out to be equal to 1.79 degrees Celsius. Now remember, that is delta TB, the change in boiling point. So the boiling point of the solution would be equal to the boiling point of pure water plus the 1.79 degrees Celsius. And the boiling point of pure water is 100.00 degrees Celsius. So we add 1.79 to that. And that would be equal to, let me put that down here. That would be equal to 101.79 degrees Celsius. And that would be the answer to that question. All right. Okay. Any questions about this? Any questions? Okay. Okay, have you all written this down? Can I clear this? Okay, let me make sure I get this thing here right. Okay, let me clear this here. And let me scroll down to the next question. So the next question says, what is the molar mass of a molecule, of a molecular solute in 9.00 grams if 9.00 grams in 250 grams of water freezes at 0.372 degrees Celsius? Okay, so let me see if you guys have any ideas as to how to deal with this one. Any ideas? What would be the first step in solving this problem? Okay, let's see here. Okay, let me ask you this to help you start off with this problem. What equation comes to mind when solving this problem?
Would you use the delta TF equals negative KFM?
Okay, very good. So let me write that down here. Okay, so delta TF is equal to what?
Negative KFM.
Okay, very good. All right. So what do we have in this question? We're given the mass of the solute, we're given the mass of the water, and we're given the freezing point of the solution. All right. And KF, of course, you'd have to be given that. And that is equal to, hold on 1 minute. KF is equal to 1.86. So let me write that down. KF is equal to 1.86 degrees Celsius over M. Okay, so we have the KF value, and we can calculate delta TF because we know the freezing point of the solution. So therefore, what can we find based on what we have so far directly?
The molality.
Okay, very good. So the molality is equal to minus KF divided by delta TF. All right. So that's minus 1 point. No, I'm sorry, it's the other way around. Let me erase this here. So the molality is equal to minus delta TF divided by KF, all right? So the delta TF would be, oh, you know something? This should be negative. That cannot be, hold on, yes. So this is a typo here. Please note that this should be negative because the freezing point of the solution will always be less than that of water, all right? So this should be minus 0.372 degrees Celsius minus 0.00 degrees Celsius, and we divide that by the 1.86 degrees Celsius over M. Okay, so let me do that calculation. So that's basically 0.372 divided by 1.86. And according to my calculation, that gives 0.200 M. All right, so far we have calculated the molality. Now, remember the question is asking for the molar mass, right? So basically, we're going to use these two things to calculate the molar mass. We're going to need the mass of the solute and the mass of the water, right? Plus, we're going to use this. So the question is, how do we tie all of these three together to solve for the molar mass, which is what the question is asking for? Now, let me give you a hint. Let me just put this over here separate. The definition of molar mass is, or can anybody tell me what the definition of molar mass is? There's an equation that you can use to calculate the molar mass. What's that equation?
Is it grams per mole of solute?
Right, mass in grams. Whoops, mass in grams divided by the moles of the same substance, right? Now we have the mass in grams of the solute. That is the 9.00 grams. So the question is, how do we get the moles of the same solute? And let me also give you another hint. 0.200 M is the same thing as 0.200 moles per kilogram of solvent. All right. Okay, so I think I've given you enough hints to help you to solve this problem. So let me hear what you guys think. What would be the next step? This is the mass of the solute. This is the mass of solvent. Whoops. Mass of solvent.
We would convert the mass of solvent to kilograms.
Okay, okay, very good. 250 grams. So we convert to kilograms by doing what?
Times the 0.2. Oh, to get it to kilograms,
Yeah.
it would be divided by 1,000.
Okay, so I would put 1 kilogram up here and then 1,000 grams down here. All right. So the gram units will cancel out. Okay, so far so good. What will be the next step?
You would be multiplying it by the 0.2 to then get moles of solute.
Exactly. So you're going to multiply that result by 0.200 moles above and 1 kilogram below. So the kilogram unit will cancel out. So let's see what this gives. 250 divided by 1,000. And then we multiply that by 0.200. And according to my calculations, this works out to be equal to 0.050 moles. So now that we have the moles of solute, what would be the next step?
Convert it, well, find the molar mass using
Okay, so the molar mass will now be equal to what?
the 9 grams divided by the 0.05 moles.
Exactly, 9.00 grams divided by the 0.050 moles. And let's see what that gives. 9 divided by 0.05. And according to my calculation, this gives 180 grams per mole. And that's how you do that. All right. Okay. I see somebody has a comment, I think, or maybe I missed it. Oh, I guess. Okay. Any questions about this? And let me just say that this method that I've just went through is actually the method that is used very often to determine the molar masses of biomolecules, especially polymer molecules like starches and, or I should say carbohydrates, I should say in general, or proteins and so on. Basically what they do is that they measure a certain amount of the substance and they dissolve it in a certain amount of water and they look at the change in the freezing point, and then they would do calculations like what we just did in order to find the molar mass of the particular biomolecule. And a similar process can be used when it comes to elevation of boiling point. Pretty much the same idea. All right. Okay. Any questions about this? Any questions? Any questions? Okay. Can I clear this? Somebody say yes or no. Okay. Let me clear this and let me do that and let me scroll down. Okay, so this one now has to do with osmotic pressure. So let me just remind you that the equation for this is pi
MRT.
is equal to MRT, exactly. And this should kind of look familiar. Well, and this should be uppercase M, RT, right? This should look familiar to you if you remember the ideal gas equation, PV is equal to nRT, right? This can be rearranged to get P is equal to N over V times RT, and N over V is the molarity, so this is for gases. The only difference between these two is that this is for solutions. So we replace pi, or I should say replace P with the Greek letter pi for osmotic pressure, right? Okay, so, oh, and by the way, just to briefly, before I even get into this, just to briefly talk about osmosis, just in case, you know, you may not understand everything clearly in the videos. In fact, let me clear this for the time being. And let me get out of this here. And let me go here. And let me get rid of all this here, right? Okay, so basically the whole idea behind osmosis is that if you have, hold on, somebody's asking a question. When we take the test, are you going to give the formulas we need? Okay, very good question. There are some formulas that you'll be given, which would be available in the tables, the same tables that I've posted in Canvas. So I'm answering a question that was put forward by Ms. McCoy. She's asking if formulas will be given, and some of the formulas will be given, all right? I don't remember which ones, to be perfectly honest, but you can consult the tables under the files link, and they will, you'll see, you know, the different formulas that will be available to you while you're doing the test. Yes, you will be given a periodic table, Ms. Rena. That's, in fact, you'll be given 2 versions of the periodic table plus a table with the periodic elements in alphabetical order, all right? Okay, any other questions before I move on? Any other questions? Okay, so the whole idea behind osmosis is that if you have this kind of hypothetical situation where you have 2 solutions separated by what is called a semi-permeable membrane, right? So this is called a semi-permeable membrane, right? What will happen is that you'll have the solvent molecules. Now we're going to assume that the solvent is water, right? And let's say that you have a solution over here, and let's say that this solution is concentrated, while the solution over here is more dilute, right? Then what's going to happen is that you're going to have solvent molecules passing back and forth between the concentrated and dilute. However, the net flow of the solvent molecules would be from the more dilute to the more concentrated, right? So basically, the net flow, let me just use this arrow here. Let me erase this here. The net flow would be in the direction shown by the arrow. So, hold on. So this would be the net flow of solvent molecules, right? Now the solute molecules would be too large to pass through those pores of the semi-permeable membrane, right? So basically it's pretty much only the solvent molecules that will be going back and forth, but the net flow would be from the more dilute to the more concentrated solution. And as a result, the 2 solutions will change in concentration. The concentration of the more dilute solution will become more concentrated because the volume of the solvent would be less, and the concentration of the more concentrated solution will become more dilute because now the solvent volume would increase, all right? So the concentration here will decrease on that side, while the concentration here will increase. Concentration will increase. All right. And that's basically what is happening in osmosis. And both solutions will change their concentration until both solutions are isotonic, right? And what that means is that the concentrations of both solutions will be the same. Okay. So that's basically the whole idea behind osmosis. And I think I covered in the video lectures an example from biology where you might have a blood cell. Let's say that's your blood cell, which has a thin semi-permeable membrane. And the concentration of the solutions here would be of a certain value, right? If you put that blood cell in an area where the environment, aqueous environment is more concentrated, while this is more dilute. Let me just put dilute here. Then what's going to happen is that you're going to have the net flow of water from inside the cell to outside, and therefore the cell will shrink. And there's a medical term or biological term for that. We call that crenation, when the blood cell shrinks. And then the opposite will happen if the cell is placed in a more dilute environment, in which case the net flow of water would be from outside to inside the cell. And then what will happen is that the cell will swell up and may even burst, right, as a result. And the term for that is hemolysis. All right, so that's just an example of the principles involved in understanding osmosis, how it applies to biological systems such as the blood cell. Okay, enough of that. So now that I've mentioned all of that, let me go to the question now, which is saying, okay, so it talks about urea. It gives you the formula, and it says that the osmotic pressure of an aqueous solution containing 2.02 grams of urea in 145 mils of solution at 20 degrees. Oh, they're asking for the osmotic pressure. Okay, so this is a pretty straightforward application of the equation. So let me rewrite the equation here, which is pi is equal to mRT. Okay, so what would you do with this? Anybody? How would you solve this problem?
You would convert grams of urea to moles,
Mm-hmm.
and then you would
Okay, so
divide-
let me write that down first. So convert the grams, 2.02 grams to moles. So how would you do that?
you would find the molar mass since they gave you the formula of urea.
Okay, okay, very good. So I have the molar mass right here. So let me just put 1 mole. The molar mass is actually 60.06. 0.06 grams. Okay, then what?
Then you would divide that answer by 0.145 liters.
Okay, 0.145 liters. And that would give you the molarity, right?
Yes.
And then what?
And then once you get the molarity, you plug it into the equation.
Okay, so multiply by R, which is 0.0821 liters atmospheres over mole Kelvin times the temperature, which is 20 degrees. Now remember, the temperature must be converted to Kelvin, all right? So that will give you 293 Kelvin, and that's it. That's a setup. So according to my calculations, when I did that, the answer became, what's that?
5.58.
5.58, exactly, 5.58 atmospheres. And that would be it. That would be the answer. All right. Okay, any
What do
questions about, oh, I'm sorry.
What do you have under the 0.821 liters atmosphere? What does that say?
Oh, the units. Okay, so this is Kelvin and this is moles, right? And the grams will cancel out here and here. The moles will cancel out here and here. The Kelvin will cancel out here and here. And the liters will cancel out here and here. So the only unit remaining would be the atmosphere unit in the end. All right. And folks, please, I don't know if I told you this before, but whenever you're doing problems of this type, make sure you set it up like I just did here. Make sure that you include the units in your setup so that you can see how the units cancel out when you're working out your final answer. All right. Okay, any questions about this one? Any questions? Any questions? Okay, is it okay for me to clear this? Okay, let me do that right now. And let me do that and let me scroll down. Okay, so this question says, and I think this is the last question if I'm not mistaken. Right, it's the last question, okay. So it says a dilute aqueous solution of an organic compound soluble in water is formed by dissolving 22.3 grams of the compound in water to form a 0.250 liter solution. The solution so formed has an osmotic pressure. Oh, I just remembered something which I neglect to mention. Osmotic pressure. I'm quite sure you saw this in the video, but let me remind you of what it is. The osmotic pressure is the pressure required to reverse osmosis. All right. So that's basically what the osmotic pressure is. So I just thought I should mention that. Okay, so continuing with the question, it says that the osmotic pressure is 2.12 atmospheres at 25 degrees Celsius. Assuming that the compound is a non-electrolyte, what is its molar mass? Okay, so how would you tackle this problem?
Wouldn't you have to rearrange the formula first?
Okay, so this is the formula right here. All right. So how would you rearrange this?
M equals pi over RT.
M is equal to pi divided by RT. Very good. Okay, so what do we do with this now?
Well, they're giving you the pi.
Okay, which is 2.12 atmospheres. R is 0.0821 liters atmospheres over mole Kelvin. And T is 25 degrees, which is the same thing as 298 Kelvin. Okay, so what does that give?
0.0867.
Let me confirm that. I'm not saying that you're wrong. I just like to confirm that. Divided by 0.0821, divided by 298. Okay, so you said 0.0867. That would be indeed correct. And the units here would be moles per liter, or M, uppercase M, because the atmospheres will cancel out, the kelvins will cancel out. So the only units here would be 1 over liters per mole, which is the same thing as moles per liter. Okay, so now that we have the molarity of the solution, what would be the next step? Now remember, the question is asking for what? The molar mass, right? And remember, the molar mass would be grams over moles. The mass in grams over the moles of the substance. Now they gave us the mass in grams already. All right. So how would you find the moles?
Would it be M times V or no?
Yeah, the molarity, the molarity, the moles, I'm sorry, would be equal to the molarity times the volume in liters, right? So the molarity we calculated to be equal to 0.0867 moles per liter multiplied by the volume in liters. What's the volume? 0.250 liters, right? So that gives, let me see here, 0.0867 times 0.250. So according to my calculation, that gives 0.0217 moles, all right? So what's the molar mass? That'll be equal to what?
Mass in grams over moles.
Okay, so the mass in grams is what? 22.3, right? Grams divided by the moles that we just calculated. And according to my calculations, this works out to be equal to 1.03 times 10 to the 3 grams per mole. And that's how that is done. All right. Okay, any questions about this example? Any questions?
I have a question. So I'm a little confused when he said it gives you pi and that's equal to 2.12 atmospheres. I'm confused on that whole concept because I thought pi was like 3.14, etc.
This pi is a different pi than that. The pi you're referring to is basically deals with the ratio of the circumference of a circle to its diameter. This pi here, if you look in most textbook, this pi would be an uppercase symbol, while the pi that you're talking about is a lowercase. All right. So this pi here is basically just a symbol that is used instead of P to represent osmotic pressure.
Okay, so it's always going to be whatever the pressure
Osmotic.
is.
Exactly, whatever the osmotic pressure is, yeah.
Is that always needing to be in atmospheres?
Not
Well, we
necessarily.
have to convert.
Exactly. It could be right. You're absolutely right. You could be given them, you could be given the osmotic pressure in other units like torr or millimeters mercury. Those are you know, other alternative units. But if you're going to use this equation, you'd have to convert those units into atmospheres. And then you plug that number into the equation.
Okay, thank you.
Will we be given the conversion factors on the exam if we're not given it in atmospheres?
Yes, you would be given, right. The same table that I referred to earlier will also contain conversion factors, which include, you know, going from atmospheres to torr, millimeters mercury, whatever.
Okay, thank you.
All right, any other questions? All right, if there are any other questions, hold off on those questions because this is our first break. So we're going to resume at 11 o'clock, all right? Okay, so we're going to restart now, but before we get into what we're going to talk about next, I just want to let you know that as far as this assignment that we just looked at is concerned, you need to make sure it's completed and submitted by tomorrow midnight. I've already opened up a Dropbox in Canvas for you to do so. So make sure that you turn it in. Now, I think I probably dealt with this before, but let me just say it again, just in case. So basically what I'm expecting is that this assignment would be done by hand, right? So it should be handwritten, not typed. Make sure that you use blue or black ink in order to complete it. Make sure it's also submitted as a PDF document. Very important. For some reason, when it comes to Canvas, downloading other formats is kind of difficult. And also write your name at the top of each page of your handout before you submit it electronically. All right. I'm going to post an announcement with all these things that are required so that you're reminded of what you should do when it comes to submitting the assignment. All right. So this assignment will be due by midnight tomorrow, right? July 4th. All right. Okay. So what I was thinking of doing now is introduce you to the next chapter, which is dealing with kinetics. So what I'm going to do is, or maybe I should share my screen first. That would be a good idea. Okay. And then let me go to the kinetics PowerPoint and download it. Okay, it's taking its time. Okay, chemical kinetics, that's what we'll be talking about today. And I've posted videos based on this already, so you'll be able to watch the rest of it if we have not completed this discussion today. So let's talk about chemical kinetics and what it's all about. So whenever you hear the term kinetics, usually it's talking about motion or something moving. In the context of chemistry, what we're concerned about when it comes to kinetics is how fast a reaction proceeds. And at this juncture, I want to talk about two very important concepts in chemistry that chemists all over are concerned about when it comes to chemical reactions. They're concerned about how fast the reaction proceeds, right? If they're studying a reaction, which is, as I said before, kinetics. And then they have this other area known as thermodynamics, which we're going to talk about later on in this course, which deals with whether or not a reaction will take place in the first place. Okay, I see some, oh, okay, I just saw some comments here. Let me deal with these quickly. So somebody was asking, we can't use pencil? The answer is no, no pencils, all right? And the reason why I'm saying that is because, especially when you're submitting stuff online, sometimes I've noticed when people use pencils, it comes out very faint and I can hardly read it, right? So that's why I said that you should use either blue or black ink, right? In order to complete the assignment. Okay, so Luis Lozano is saying, can I use my iPad to download it and write it? Oh, okay. Yes, you can do that too, Louis. That's fine by me. I know some students have done that in the past, and I've had very little issues with that. But make sure it's a PDF document when you submit it. And Ms. McConnell, oh, you said that you have done it in pencil. I would strongly suggest that you do it over in pen. Again, for the reasons I mentioned earlier. All right. Okay. So going back to our discussion here. So these are two things that chemists are concerned with when it comes to chemical reactions, right? Thermodynamics, which deals with whether or not a reaction is taking place, or if the reaction can take place. Because of course, by virtue of the fact that you'll be able to write down an equation for the reaction doesn't necessarily mean that the reaction will take place. And a lot of it depends on the conditions, right? And then if we establish that a reaction has taken place, then the next thing that we may be concerned about is the speed of the reaction. And in this context, you can have situations where the reaction proceeds very slowly. And when I say slowly, like millions of years, and then you can have the other extreme where the reaction is instantaneous. So that's basically what kinetics is all about, basically dealing with reaction speeds and how can we explain why is it that certain reactions proceed at a fast rate and others do not, all right? So at this juncture, I want to introduce to you the concept of reaction rate, right? And as stated here, the reaction rate is the change in the concentration of a reactant or a product with time. And you'll notice that they put the units here as m/s. Now, even though that is indeed possible, you can also have the units being expressed in other units of time. And also other units of other units which can be related to concentration, right? So the units here could also be m/minutes or m/hour. It all depends on, again, the speed of the reaction, all right? So let's say we have a hypothetical reaction A going to B, all right? Very simple reaction. Then we can express the rate of the reaction in terms of the change in the concentration of the reactant A, all right? And that is represented by what you see right here. So I don't know if you're familiar with this symbol in math, this small triangle. It's actually a Greek letter, delta, right? So this is change in concentration of A divided by change in time, all right? And you'll notice that there's a negative sign here. And the reason why there's a negative sign there is because the change in the concentration of A is negative because the reactant is being used up. So therefore, in order to express the rate in terms of the concentration of A, we have to put a negative sign here because A is a reactant, all right? Another way of stating the rate is that symbol right here. Rate is equal to change in the concentration of B over change in time, all right? So in this case, the change is positive because the concentration of B will be increasing as the reaction is progressing, all right? So those are just two ways of expressing the rate, and which one you choose to use is largely dependent on convenience, to be perfectly honest. There are some reactions which lends itself to measuring the concentration or the amount of reactants, and there are other reactions where, based on the properties of the product, that would be the most convenient product or substance to monitor while you're looking at how fast the reaction is going. All right. So this is just reiterating what I said earlier, because the concentration of A decreases with time, then the change in concentration of A is negative. And that's the reason why we put a negative sign here in order to express the rate. Okay. Let me get rid of this right here. Okay. So we're going to look at this reaction, this hypothetical reaction, in a bit more detail in order to further our understanding of reaction rates. So let's say we have A going to B, all right, as we said before, and we're going to have some boxes here to represent what's happening in the reaction vessel. So the black spheres would represent A, and the red spheres would represent B. So you'll notice as time progresses, what happens? The amount of black spheres becomes less and less, and the amount of the red spheres starts to increase, right? So basically, the concentration of A falls while the reaction is proceeding, and the concentration of B increases. And we can actually make a plot of the changes that are taking place in this reaction, which is shown here in this table right here, where we have the number of molecules plotted on the y-axis versus time on the x-axis. And you can clearly see that there's a smooth line here, which shows the increase in the number of B molecules. And at the same time, you see this slope right here, this other line, the black line here, which shows you the decreasing number of molecules of A as time progresses, all right? And this is what is generally observed in most reactions. So as we said before, we can say or express that the rate of the reaction can be expressed as minus the change in concentration of A over change in time, or we can express it as a change in concentration of B over change in time, all right? Okay, so just to give you a real chemistry example of reaction rate or changes in concentration as time progresses, what we're looking at here is a reaction between bromine and formic acid, all right? And as you can see, you're starting off with a very red-colored solution, right? That red-colored solution is actually due to the bromine that's present. And as you can see, as the reaction progresses, right, what happens? And by the way, let me mention also that the formic acid is colorless and the products here are colorless, right? So any change in color would be due to the change in concentration of bromine. So as you can see here, as the time progresses, what happens? The intensity of the color decreases correspondingly until the solution becomes totally clear, which implies that there's no more bromine left at the end of this reaction, all right? Now, in this particular case, it is convenient, more convenient for us to measure what we call the absorbance of bromine because of its color. There's an instrument that we use to measure absorbance. It's called a spectrophotometer. And just to give you a simple idea about how it works, basically what you do is pick a light source, and in fact, they're designed such that you can change the wavelength of the light that you're using. So basically, you have to choose the wavelength of light that the bromine will absorb maximally. And that can be obtained by using this particular plot right here of absorbance versus wavelength. And you'll notice that the maximum absorbance here for bromine is about 400, it's actually 393 nanometers, all right? So basically what you do if you were working this instrument is that you would adjust the wavelength of the light source to 393 nanometers, and then you allow a beam of that light to pass through the solutions, and then the absorbance will be measured by the detector on this side, right? And therefore, by looking at the concentration, or I should say, by looking at the changes in the absorbance as measured by the detector, you can basically monitor the reaction and actually determine the reaction rate. And the reason why we can do that is because the absorbance of the solution is directly proportional to the concentration of bromine that is present, all right? So as stated here, the change in concentration of bromine would be directly proportional to the change in the absorption of the bromine in the solution, all right? So this is just one example of how we can monitor the changes in the concentration, in this case, by monitoring the change in color. And in other cases, you'd have to monitor some other properties, all right? Okay, so let's delve into this reaction a bit further. So somebody did this experiment and collected this data. So the data that you're looking at here is the concentration of bromine as time progresses, right? So at 0, the concentration was 0.0120, and then after 50 seconds, the concentration decreases to 0.0101, and so on and so forth, right? So when you plot concentration on the y-axis versus time on the x-axis, this is the result. You get a smooth curve, all right? And what you'll find is that you can determine what is known as the average rate of the reaction, which would be the rate over a particular time frame, all right? Now, the average rate formula in this particular case would be equal to the change in concentration of bromine divided by the change in time. And of course, you have a negative sign here again because the bromine concentration is decreasing. So the change in the concentration of bromine will be negative. So if we choose 2 particular points in this graph, we can determine the change in the concentration of bromine by subtracting the initial value for the concentration from the final value. And similarly, in the case of the change in time, similar. T final minus T initial, all right? So basically, we can choose 2 points on the curve, find out the corresponding final and initial concentration values and time values, and plug them into this equation, and you can determine the average rate over a particular period or time frame. So for example, if I were to use these 2 points here, 2.96 times 10 to the minus 5, and the time here would be about 100 and something, I don't know. I would estimate this to be about 105. And then here, 2.09 times 10 to the minus 5. In this case, I would say that this is about 200, it looks like, right? Then basically, let me see if I can do the math here. I'm going to see if I can squeeze it. Come on. Okay, so I'm going to see if I can squeeze it somewhere here. So let's say, as I said before, I'm choosing this data point here and this data point, right? So the average rate would be equal to, so let me put average rate would be equal to, so the final value would be, well, let me put a minus sign first, and then the final value would be 2.09 times 10 to the minus 5 m over s minus the initial value, which is 2.96 times 10 to the minus 5 m over s, and then I'll divide. Oh, no, I'm sorry. I just realized something. I'm using the wrong values here. I assume that those values are the concentrations. Those would be the rates. So let me erase this here. What I should be using, hold on 1 minute. Okay, what I should be using are the table values here. So let me use these 2 values right here. All right, so the average rate would be equal to, this would be the final, which would be, put the minus sign first, and then I'm going to put 0.0101 m minus the initial value, which is 0.0120 m, and then I would divide that by the change in time. The change in time would be 50.0 seconds minus 0.0 seconds. And then whatever that works out to be, that would be the average rate over the first 50 seconds of the reaction, all right? So that's basically how you calculate the average rate. Now, there's another rate value that's important, and in fact, I would say it's more important, and that is known as the instantaneous rate. So the instantaneous rate would be the rate of the reaction for a specific instance in time. Now, what do we mean by that? Basically, what that means is that you choose, let's say you want to find the instantaneous rate at this point right here, right? Which is calculated to be equal to 2.96 times 10 to the minus 5. Basically, what you do is find the slope. And you all should know from your previous math experience, to find the slope of a particular point on a curve, you basically draw a tangent line that touches that point and then find the slope of that line. And that would be the instantaneous rate of the reaction at that point in time, right? And I'm quite sure you're familiar with calculating the slope. That's rise over run. In this case, the slope would be negative, again, because the concentration of bromine is falling. So therefore, that's how you determine the instantaneous rate. And as you can see, the instantaneous rate is not constant because the slope changes. The instantaneous rate is 2.96 here times 10 to the minus 5, and then it decreases to 2.09 times 10 to the minus 5, and so on and so forth. All right, which is, you know, not always true. Sometimes there are a few instances where the instantaneous rate remains the same. All right, and we're going to get into that later on. Okay, so it's very important that you know and understand the difference between the average rate and the instantaneous rate. The average rate is basically the rate over a particular time frame, where you find the difference in the changes in the concentration of the reactant or product divided by the change in time over that time frame. That's the average rate, while the instantaneous rate would be the rate at a particular instance in time. And the way you determine that is by finding the slope of that point by drawing a tangent and finding the slope of that tangent. All right. Okay. So that's basically how that is done. Any questions so far? Any questions? Any questions? Okay, so what I'm going to do next is, hold on 1 minute. Let me clear this first. Okay, and let me get over this here. So we're going to look at this reaction in more detail in terms of what we can do with the data that we have, all right? Well, we did one thing with the data already. We plotted the concentration versus time, and we looked at the instantaneous rate and the average rate. Now, what we're going to look at here is, okay, so this is the original set of data that we have for the two columns at the extreme left, all right? So the third column here gives the instantaneous rate at each of these times. So the way these values are obtained is by what I just described. For each of these data points right here on the graph, they found the slope and measured the average. Well, they found the slope of each of those points, and these are the values right here, right? And then what they did was that they looked at the relationship between the concentration of bromine and the rate, and what they find is that if you divide the rate by the concentration of bromine at each of these instances, you'll find that K is a relatively constant value, right? And in fact, if you plot these values here, or I should say these values here versus a concentration, this is what you're going to get. You're going to get a smooth line where all the data points fall almost, if not exactly, on the data on the line, all right? So what this shows us in this particular case is that the rate of the reaction is directly proportional to the concentration of bromine, all right? And that is true for a lot of reactions, but again, what you'll find is that this is not true for all reactions. There are some cases where the rate of the reaction is not directly proportional to the concentration of bromine, or concentration of reactant, I should say. So we're going to talk about those examples later on. So we can rewrite this expression in the form of an equation where we say the rate is equal to K times the concentration of bromine. So K would be the constant of proportionality between the rate of the reaction and the concentration of bromine. And we can also rearrange that equation to get K is equal to rate divided by the concentration of bromine, which is what is done to create the fourth and final column in this table right here. And as I said before, as you can see, the value of K is relatively constant, varying from 3.48, that's the lowest value, times 10 to the minus 3, to a maximum of 3.51 times 10 to the minus 3. So for all intents and purposes, we can say that K is constant for this reaction, all right? Now there's a name given to that constant of proportionality. It is called the rate constant, all right? So basically what we would have done in terms of determining the rate constant for the reaction is to average all those values. And when you average them, you're going to get 3.50 times 10 to the minus 3 seconds to the minus 1, all right? So that's basically how bromine, that reaction with between bromine and formic acid, that's basically the results in terms of looking at the rate of the reaction with respect to the concentration. Okay, here's another reaction here. This reaction is a decomposition of hydrogen peroxide to form water and oxygen, all right? And in this case here, again, as I said before, it's a matter of convenience as to what substance you monitor in order to determine the rate of the reaction. In this case, the substance that we're monitoring here is the oxygen. And we can monitor the amount of oxygen by measuring its pressure. And that's what this setup here is all about. Here is where the reaction is taking place. The oxygen is produced, and therefore it is guided by this hose into the manometer, an instrument that you should have learned about in general chemistry 1. And basically the manometer is used to measure the pressure by looking at the difference in the mercury levels in this U-shaped tube. I'm not sure if you can see it clearly here, but this is a U-shaped tube, all right? So basically what you do is look at the height difference between the mercury levels on both sides, and that gives you the pressure of the oxygen that's produced. And we can use the oxygen, or we can use the pressure of the oxygen to monitor the production of oxygen, because the pressure is directly proportional to the concentration. We know that because of the ideal gas equation. PV is equal to nRT, an equation that you should be familiar with. And we can rearrange this equation to get PV is equal to N over V times RT, which would be equal to the concentration of oxygen times RT. So basically, we can basically get an idea as to how the concentration of oxygen changes by monitoring the pressure of the oxygen that is produced, all right? In fact, we can calculate directly the concentration of oxygen once we know the pressure by rearranging this equation here to get the concentration of the oxygen. And therefore, we can determine the rate of the reaction based on the change in the concentration of oxygen by monitoring change in the concentration, or I should say the pressure over time, right? So basically, this is the relationship between the rate of change of oxygen in terms of concentration and the rate of change of pressure over time, all right? So that's basically how that is done. And based on that experiment, this is the data that has been obtained. They plotted the pressure versus the time right here. And again, you can see it's a smooth curve. And you can determine the instantaneous rate in pretty much the same way as we did before by drawing a tangent touching that line or touching the curve and finding the slope of that line, rise over run, and that will give you the slope, which gives you the instantaneous rate at that particular time. All right. So that's basically how we determine the relationship between the rate of the reaction, or I should say the changes in pressure versus time for this particular reaction. Okay, let's talk about reaction rates and stoichiometry. And then after this, I think we should be able to tackle some questions from the next assignment. Let me just check something here first before I move on. So let me see here, assignments. Okay, so I'm about to publish assignment number 2 right now. Okay, so I've published assignment number 2. And let me see here. Okay, so let me see here. All right, so let me continue our discussion. So now we're going to look at the relationship between reaction rates and the stoichiometry of the reaction. And we're going to start off by looking at this hypothetical example where we have 2A reacting to form B. So basically, the mole ratio between A and B in this particular case is a 2-to-1 ratio. All right. So based on that stoichiometry, we can conclude that 2 moles of A will disappear for every 1 mole of B that is produced, right? Because of that 2-to-1 mole ratio. So therefore, we can write down that the rate of the reaction can be expressed in terms of the change in concentration of A versus T, right? Versus change in T, right? But that is, you can set that to be equal to this as well, keeping in mind the 2-to-1 ratio. Now remember, for every 2 moles of A that disappears, for each mole of B that is formed, right? So therefore, that's why we have this half right here, minus half, right? Minus because A is being used up, and therefore 1/2, because for every 2 moles of A that disappear, the 1 mole of B would be formed, right? So basically, we can set this being equal to this. What this is saying basically is that the rate of change of B, or I should say the rate of change of, how should I put this? The rate of change of B, or the rate of change of B in this reaction would be equal to minus half the rate of change of A in the same reaction because of the 2-to-1 ratio. So extending that to this hypothetical example, where the lowercase letters represent the coefficients and the uppercase letters represent the actual substances. Then we can write down a relationship between the rate of change of each of these substances involved in this reaction. And that is this equation right here. All right. So you'll notice that in each of these terms here, we have the change in concentration of the different substances, the reactants and the products, right? You also have negative signs here as far as the reactants are concerned. There are no negative signs when it comes to the products. Also, in each case, we have 1 divided by the coefficient of the substance for which we have the rate term right here. So in the case of the first term here, where we have lowercase a here, then we have 1 over a here, where we have lowercase b here, 1 over b, and so on and so forth, right? So this equation here basically relates the rate of change of all the different substances to each other, all right? And you can apply this pretty much literally to any equation. Once you know what the stoichiometry is, then you can find out the rate of change of one substance compared to that of another substance, all right? So that's a very important relationship that you need to be aware of, all right? So just to give an example, let's look at this question. It says, write the rate expression for the following reaction, and it gives you the balanced equation, right? So basically what they're asking for is something similar to what we just looked at. So basically, you'll notice that you have a coefficient of 1 here for methane, you have a coefficient of 2 here for oxygen, you have a coefficient of 1 here for carbon dioxide, and a coefficient of 2 here for water, all right? So basically, we can write this down. The rate of the reaction will be equal to minus the change in concentration of methane divided by the change in time. Again, we use a minus sign here because methane is being used up, and that would be equal to minus half the change in concentration of O2 divided by change in time. And the reason why we have a half here is because we have a coefficient of 2 right here, right? We have 2 here, so therefore that means that we need to have a 2 down here, 1 divided by 2 here. And then we get to the other side. Carbon dioxide is a product, so therefore the term for that would be the change in concentration of carbon dioxide divided by change in time. And then as far as the water is concerned, you'll notice that there's a coefficient of 2 here. So therefore that means that the term for the water would be half times the change in concentration of water divided by the change in time, all right? So that's how you determine the relationship between the changes in concentration or the rate of change of concentration of the different substances involved in a reaction. All right. Okay, so based on what we have just discussed so far, we can look at a couple of questions from the next assignment. Okay, so let me do this. Let me do that. Let me do this. Assignment 2. Download it. Okay, and let's see what we have here. Okay, so, all right, so the first question is, when starting a reaction, the concentration of one of the reagents is 1.50 m. After 3 minutes or 3.0 minutes, the concentration of the reagent is 0.85 m. Using these data, determine the average rate of this reaction in m per second, all right? Now remember, the average rate, let me, the average rate, let me write this down here just to help you guys, would be equal to the change in the concentration of the reagent, I'm going to call it A, divided by change in time, and that would be equal to the final concentration of A, I'm going to put final here, minus the initial concentration of A, I'm going to put that here, divided by T final minus T initial, all right? Okay, so now that I've helped you so far, what do you think would be the next step? Anybody? What would be the next step?
You would take 8.5 M minus 1.50
that-
M.
I'm sorry, not to cut you, but I forgot something which is really important. Can anybody tell me what that is? I forgot to put something that is really
sign.
important. I'm sorry?
The negative sign?
Exactly, the negative sign. Thank you. Right? So this should be negative here. All of this should be negative. Okay, so I don't know who was speaking a while ago. Who was it? Who was
It
the
was
young
me.
lady who? Okay, Miss McCoy. All right, so you were saying what now? Minus,
8.5 M, or I'm sorry, 0.85 M minus
Mhm.
1.50 M.
minus 1.50 M. And then divided by what?
Divided by 3.0 minus 0.0.
Okay, minus 0.0 minutes. But remember, the question says that the rate must be given in meters,
per
not meters, I'm
second.
sorry, M over second, right? So what do you think we need to do next?
Multiply by 60.
Okay, yep. So this part here, I would multiply by 60 seconds over 1 minute. All right, so that the minute units will cancel out. So you'll be left with the second units in the long run, in the final answer. And let me see here. One minute. Okay, what in the world is going on here? Okay, let's see here. Okay, so according to my calculations, the answer I got, and you can tell me if I'm correct or not. I got 3.6 times 10 to the minus 3 M over S. All right. And that's basically how that is done. Okay, any questions about this particular problem? Any questions? Any questions? Okay, now is it okay for me to clear this? Okay, hold on. Okay, so let me clear this. Let me get out of this and let me scroll down. Okay, now this one, okay, tell you what, because this is basically repeating the same thing. We're just going to ignore the B part, and just do the A part. So the question says, use the table of data shown below to calculate the average rate of the reaction. And in the case of A, between 10 seconds and 30 seconds. Okay, so how would you tackle this one? Excuse me. Anybody?
We can write it out first.
Write out what?
Uh,
Write
before
out what
we would have
exactly?
negative- Would it be negative 1/2 for the first part for the concentration of NO?
No. What's the formula for calculating the average rate? That's the first thing I want to ask you. We just used it a while ago. Average rate.
Negative delta A over delta T.
Well, in this case, we're going to use NO. So negative change in the concentration of NO divided by change in the time, right? Now, the question says that you have to calculate the average rate over this period of time. 30 seconds, between 10 seconds and 30 seconds, right? Okay, so how would we set this up? Minus what?
0.073 minus 0.124. Or 0.110, sorry.
Okay, so this will be M and then 0.110 M divided by what?
30 seconds minus 10 seconds.
30 seconds minus 10 seconds, exactly. So when I did that calculation, I got, and again, please check behind me to make sure I'm doing it right, but this is what I got. 2 times 10 to the minus 3 M over seconds. All right. Okay, any questions about this one? Any questions? Okay, can I clear this? Okay, so let me clear it then. All right, let me do this. Let me scroll down. Okay, now the next question is kind of interesting because this is where we're going to apply what we just learned in relation to the stoichiometry, in relation to the rate of the reaction.
Professor
Oh,
Nicely,
Yes, ma'am.
I got a different answer on my calculator for some reason.
Okay, what did you get?
I got 1.9
Oh,
times
see,
10 to the negative 3.
yeah, so what I did was run it off to 1 sig fig. And the
Oh,
reason
okay.
why,
Okay.
right, the reason why is because the 20 minus 30 gives you, what was it? Gives you, I'm sorry, the 30 minus 10, is it 30 minus 10? Let me look at it again. Right, the 30 minus 10 gives you 20. 20 is 1 sig fig.
Oh, right,
So-
right. Thank you.
So you just round off to 1 sig fig in your answer, okay? All right, so as I was saying, this particular question now gives you, it deals with the stoichiometric relationship between the substances and how it affects the rate of change for the different substances involved. So they gave you a balanced equation here, right, for the reaction. And it says that the rate of formation of NO2, which is one of the products, is 4.0 times 10 to the minus 3 mole per liter per second, right? Now, what they have given you actually, hold on, I just noticed, okay. So what they have given you actually is, let me write this down. They gave you that the change in the concentration of NO2 over change in time is equal to 4.0 times 10 to the minus 3 M over S, right? That's basically what they gave you, right? So the first question is asking for you to calculate the rate of disappearance of N2O5. Now you'll notice that there's a 2:4 ratio between the N2O5 and NO2. So the relationship between them would be minus 1/2 times the change in concentration of N2O5 over change in time is equal to 1/4 times change in concentration of NO2 over change in time, right? So this 2 here comes from the coefficient of 2 in the case of N2O4, and this 4 here comes from the coefficient of NO2 right here, right? Now, what the question is asking for is this right here, all right? So basically, we know what this is already because that's this right here. So therefore we can put this being equal to 1/4 times 4.0 times 10 to the minus 3 M over S. And this is equal to 1.0 times 10 to the minus 3 M over S. So therefore, the rate of change of N2O5 would be equal to minus 2 times 1.0 times 10 to the minus 3 m over s, which is equal to 2.0 times 10 to the minus 3 minus m over s, right? So that would be the rate of change of N2O5. Now, please note the question is asking for the rate of disappearance. So therefore, we can say that the rate of disappearance is equal to 2.0 times 10 to the minus 3 m over s. All right? And that's basically how that is done. All right? Any questions about that one? Any questions?
Is the rate of disappearance always going to be positive or
Yeah,
okay?
because the negative indicates the rate of change.
Okay.
You see what I'm saying? So
Yes.
therefore, when we're talking about the rate of disappearance, it would simply be the absolute value, 2.0 times 10 to the minus 3.
Okay, thank you.
Yeah, all right. Okay, any other questions before I clear this? Any other questions? Okay, so is it okay for me to clear this? Okay. So clear it I shall. All right. So let's see if you can do this on your own. Calculate the rate of appearance of oxygen. Let me scroll down a bit here. All right, so let's see what you can come up with in answer to this question. If you understood what we did in A, you should be able to do the B part. Well, let me ask you this. Let me help you guys out. So what would be, well, let me remind you of something. Let me remind you that, scroll down here, write it down here. Okay, let me remind you that according to the question, the information given in the question, the change in concentration of NO2 over change in time would be equal to 4.0 times 10 to the minus 3 m over s. All right, so that's what the question gave you, right? So what the question is asking for in this case is the rate of appearance of oxygen. So based on the balanced equation, what is the relationship between the rate of appearance of NO2 and the rate of appearance of oxygen?
Four to one.
Okay, so how would you express that?
1/4
1 over 4?
the change in concentration NO2 over change in time.
Okay. Over change in time. And that would be equal to what?
Change in concentration oxygen over change in
Okay,
time.
exactly. Very good. All right, so what would be the next step? Now that we have established that relationship, what's the next step?
Plug in the 4.0.
Okay, so we're going to have 1 over 4 here times 4.0 times 10 to the minus 3 m over s. And that's it. The answer becomes 1.0 times 10 to the minus 3 m over s. And that's basically how that is done. All right. Very good. So far, so good as far as this chapter is concerned. All right. So we're going to take our next 10-minute break and resume at 12. All right. Okay, so I am back. So we're going to talk about the relationship when it comes to reaction speeds, kinetics, whatever you want to call it, between the rate of a reaction and the concentration of the reactants. And there's a term for that. It's called the rate law, all right? So the rate law is the relationship between the rate of the reaction to the rate constant, which we were introduced to earlier, and the concentrations of the reactants that are raised to some powers, all right? So the rate law is basically a mathematical equation. So let's say we're going back to the hypothetical reaction, which we talked about earlier. Then the rate law for this reaction is given by this equation. Rate is equal to K times the concentration of A raised to some power X times the concentration of B raised to some power Y, all right? Now, the different terms here, I need to explain what they are. The X represents the order of the reaction with respect to A, all right? So basically we say that the reaction is Xth order with respect to A. And then we can similarly say something about Y, which is the order with respect to B, all right? And then there's another term which is called the overall order or the total order, which would
Sorry
be
to interrupt. We
Oh.
can't see your screen.
Oh, I'm sorry. I'm sorry. I'm so sorry. I'm so sorry. I keep forgetting to do that. Okay, so this is what I was talking about here. So let me just briefly recap what I just said. The rate law is a relationship between the rate of the reaction and the concentration of the reactants, where the concentration of the reactants are raised to some power. And this is the hypothetical example, and this would be the rate law for that reaction. So as I was saying, based on this expression right here, right, which says rate is equal to K times the concentration of A raised to the X times the concentration of B raised to the Y. So we can say that the reaction is Xth order with respect to A and Y order with respect to B. And then I was about to say that the total order is the sum of the individual orders. So in this case here, it's X plus Y, all right? And for our purposes, the values of X and Y will be equal to, will be equal to X and Y will be equal to 0, 1, or 2, all right? Now, we can have some other numbers as well, but that's a bit beyond our scope at this level, all right? Okay, so pretty much all the values of X and Y, the orders of a reaction with respect to certain reactants will be equal to 0, 1, or 2, all right? And we're gonna learn how to determine what those values are, because one key thing that you need to keep in mind, and I think I mentioned it later on, is that you cannot tell what the order of the reaction is just by looking at the equation, all right? But we'll get to that later on. So let me get out of this here and go back to my, okay. So let's look at this example right here. In this case, we have this reaction right here, and somebody did some data collecting in terms of how the concentration affects the rate of the reaction. So this is basically what the result is. And basically we can tell what the order of the reaction is based on the data that's provided. In fact, that's the only way we can tell what the order of the reaction is. So let us look at comparing the different terms or rows to see if we can determine how the rate affects, how the concentration changes affect the rate. Okay, so let's compare the first two, all right? Let's compare experiment 1 and experiment 2 right here, right? Now you'll notice that between 1 and 2, the concentration of fluorine remains constant, but the concentration of the chlorine dioxide is quadrupled, all right? So any effect on the rate or any effect on the rate will be due to the change in this and not any change in the flow rate. And what do we notice about the rate change? It was 1.2 times 10 to the minus 3. It is now 4.8 times 10 to the minus 3 when the concentration of ClO2 is quadrupled. In other words, the rate quadrupled as well. So what does that tell us? It tells us that the rate of the reaction is directly proportional to the concentration of ClO2. All right. So let me do this here. So as you can see here, as I stated before, when the concentration of ClO2 is quadrupled, with the fluorine concentration constant, the rate is quadrupled. So what that tells us is that the rate of the reaction is directly proportional to the concentration of ClO2, which means that the order of the reaction with respect to ClO2 is 1, all right? So therefore, the Y, which is the order of the reaction with respect to ClO2, would be equal to 1. Now, if you compare experiment 1 and experiment 3, you'll notice that the concentration of fluorine is doubled, while the concentration of ClO2 remains the same. And what effect does that change in the case of fluorine? What effect does that have on the rate of the reaction? Initially, it was 1.2 times 10 to the minus 3 when the concentration is 0.10. Now it is 2.4 times 10 to the minus 3 when the concentration is 0.2. So again, what you find is that the rate of the reaction is directly proportional to the fluorine concentration, because as the fluorine concentration is doubled, so does the rate. So what does that mean? That means that the order of the reaction with respect to fluorine would be 1 as well, all right? So therefore, the rate law of the reaction in this particular case is rate is equal to the concentration, is equal to K times the concentration of fluorine times the concentration of ClO2, all right? So that's basically a very simple example of how we can determine the rate law based on rate data, how the rate changes with the change in the concentration of the different reactants, keeping one fixed, all right? So that's basically how we do that. Let me check the comments here. Oh, okay. All right, so let's talk about some things about rate laws that you need to be aware of, especially when it comes to solving problems. First thing I want to say about rate laws is that the only way to determine the rate laws is by performing an experiment. So you have to perform experiments where you look at the effect that the rate, that the concentrations of reactants will have on the rate of the reaction. There's no other way to determine it. You cannot just look at the equation and tell what the rate law is, all right? The reaction order is always defined in terms of reactant and not product concentrations, right? So, and that's because the rate law is basically a function of the concentration of reactants and not the products, all right? The third thing I want to say is, and this is related to the first item here, the order of the reactant is not related to the stoichiometric coefficient of the reactants in the balanced equation. So in other words, you cannot just look at the coefficients of the reactants and declare them to be the order. As I said before in the first line, the only way you can determine the rate equation or the orders of the reaction with respect to the different reactants is experimentally. So for example, in the reaction that we looked at, the reaction between fluorine and ClO2, you'll notice that it's a 1:2 mole ratio between the fluorine and the ClO2, right? There's a coefficient of 2 here and a coefficient of 1 here, right? But when you determine the rate law, what do you notice? There's no 2 here, right? So therefore, there's no real direct relationship between the coefficient and the order of the reaction with respect to the particular reactant, all right? So that's why I keep saying that you cannot tell what the orders of the reaction is just by looking at the equation. You have to carry out the experiment, get your data, and then do the processing of the data so that you can figure out what the orders of the reactions are with respect to the reactants, and then determine the rate law based on that, all right? Okay, so what I want to do is show you this example right here. Now, this question says you're to determine the rate law and calculate the rate constant for the following reaction from the following data, all right? And it gives you the equation and it gives you the table with the data, all right? So basically what you need to do is find the rate law for this reaction. Okay, now because I'm going to need space, I'm going to move away from this. So you may want to, I don't know, if you could download the PowerPoint. And somebody mentioned earlier that they could not obtain the PowerPoint from Canvas. Let me see if I can rectify that. Hold on 1 minute. Okay, so lecture notes. Okay, it should be available. I don't remember who made that statement or asked that question. But if you go to files and go to lecture notes, right, you're going to see the kinetics chapter handout or PowerPoint is available there. All right. So you may want to, for the rest of you guys, you may want to download that so that you can refer to it, because I'm going to need some space in order to tackle this problem. All right. Okay, so what I'm going to do is, 1 minute. Okay, so what I'm going to do is I'm going to get out of this here, and I'm going to bring up my writing application here, and I'm going to tackle the problem here. Okay, so basically the question gives us the data table, and it's asking for you to determine the rate law. So this is the first thing I would write down. I would write down rate is equal to K times the concentration of S2O8 2-, which is called the persulfate ion, raised to the X power times the concentration of I-, raised to the Y power. All right. So basically, we need to find out what X is, and we need to find out what Y is based on the data. All right. So what I'm going to do now is write down an equation where the data for experiment 1 would be plugged into this equation right here. All right. So according to experiment 1 in the data table, the rate is equal to 2.2 times 10 to the minus 4 m over s, and that is equal to K times the concentration of the persulfate, which according to the table is 0.08 m raised to the X, times the concentration of I-, which is 0.034 m raised to the Y. All right. So that's for experiment 1. And then I'm going to do something similar for experiment 2. For experiment 2, I'm going to put the rate, which according to the table is 1.1 times 10 to the minus 4 m over s, is equal to K times the concentration of persulfate, which is 0.08 m raised to the X, times the concentration of I-, which is 0.017 m raised to the Y. All right. And then what I'm going to do next is divide the top line by the bottom line. And in doing so, I will be able to cancel out things that are common to the numerator and denominator, such as the K's, the 0.08 raised to the X, and pretty much all the units will cancel out here, 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 and here, okay? And the 10 to the minus 4 will cancel out here and here as well. So what are we left with? We're left with 2.2 divided by 1.1 equal to 0.034 divided by 0.017, all raised to the Y. Now 2.2 divided by 1.1 will give you 2, and 0.034 divided by 0.017 will give you 2. So this will be 2 to the Y. So that means that Y is equal to what? What is Y equal to?
1.
Exactly. All right. So we have found out the order of the reaction with respect to I-, right? So Y is equal to 1. Okay. So, do you need some time to write this down, folks? Let me know when I can erase it. Okay, so let me remove all of this here. Okay, so the next thing I'm going to do is I'm going to compare, I'm going to do something similar to what I just did. The only difference is I'll be doing it between experiment 2 and 3. And the reason why I'm doing it between experiment 2 and 3, if you look at both of them, you'll see that they both have the same concentration of I minus, all right? So for experiment 2, the rate would be equal to K times 0.08 m raised to the x. And I just realized I made a mistake. I should put the value for the rate here. So let me erase this value here. And the rate according to the table for experiment 2 is 1.1 times 10 to the minus 4 m over s, all right? And then continuing over here, the concentration of the I minus would be 0.017 m raised to the y, all right? And then now for experiment 3, the rate is equal to 2.2 times 10 to the minus 4 m over s, and that will be equal to K times 0.16 m raised to the x times 0.017 m raised to the y. And I divide the top by the bottom. And what do I notice? I can cancel out these here. The k's will cancel out. And these units will cancel out. The 10 to the minus 4 will cancel out here and here. And we're left with 1.1 over 2.2. And that would be equal to 0.08 divided by 0.16, both raised to the x, right? And therefore, this would be 1 over 2. This would be 1 over 2 raised to the x, which means that x would be equal to 1. So in this particular case, it turns out that the order of the reaction with respect to each of them would be 1, all right? With respect to each reactant. Okay, so I don't think I need to erase this. I think I can continue over here. Okay, so far we have determined the orders. Let me see here. Oh, we need to calculate the rate constant, K. How do we calculate K? Well, it's actually very simple. First thing I'm going to do is write down the rate law with the orders that we determine, and that's rate is equal to K times the concentration of S2O8 2 minus times the concentration of I minus. All right, so that's basically the rate law, right? So to find K, we can just do some algebraic rearrangement to get rate is equal to, or rate divided by concentration of the persulfate times the concentration of I minus. And then all we have to do now is plug in values for the rate and the concentrations from the table, right? And you can choose any one of the experiments values to do this. So if I choose experiment 1, all I have to do is put the value for the rate, which is 2.2 times 10 to the minus 4 m over s, divided by, for the persulfate, that is 0.08 m, times, for the iodide, that would be 0.034 m, and that's it. Whatever this gives, that would be the answer. So let's see what that gives. 2.2 times 10 to the minus 4, 2.2 times 10 to the minus 4, 2.2 times 10 to the minus 4, divided by 0.08, divided by 0.034, And according to my calculations, I would round this answer off to 1 sig fig, so that would be 0.08. And in terms of the units, well, this m will cancel out with this m. So basically the units for this would be m to the minus 1, s to the minus 1. And that would be the rate constant. All right. So that's basically a typical, this is basically a typical rate law type of question. All right. And whenever you're solving problems of this type, I want you to take pretty much the same approach. All right. Okay. So any questions about this before I move on? Any questions? I see, hold on, I see two. Okay, so somebody's asking, do we have to give the overall rate law? Well, it depends on what the question is asking for, right? So if the question is asking for the rate law, then yes. No, I don't know if you're talking about the rate law or the order, the total order. But again, it depends on what the question is asking for. If you're doing a question where it's asking for the order for each reactance and the total order, then that's basically what you have to calculate. In this particular case, the total order would be 1 plus 1. Let me write this down. Total order would be 1 plus 1, which is 2. In this particular case, all right? Okay. Any other questions? Any other questions?
Professor Nicely, if we were
Yes,
doing this
ma'am.
on a test, would we have to write out everything that you just did? Or if we know how to write it in a shorter way because we know things are going to cancel, can we do that instead?
Well, I don't know. What do you mean by a shorter way? Like what?
Like when I looked at the graph, I could see that when S208, when that was doubled, I could
Mhm.
see that the rate was doubled, and I could see the same for the other one. So then you would know a lot quicker than doing out all this work that the order was 1.
Well, the reason why I'm showing you this way is because there are some questions where it is not so obvious. All right.
Okay.
So my recommendation would be to basically go through this. You won't go wrong. I mean, I know it's kind of longer and all that, but you won't go wrong if you do it this way. Because there's
Points
some
marked off.
well, let's put it this way. If you get your answer wrong, then it definitely would hit you hard in terms of your score.
But if it was correct.
If it is correct, then yeah, I'll give it full credit.
Okay. Thank you.
Okay. Any other questions? Any other questions? Okay. Let me see here. Okay, let me scroll down. Okay, you won't be able to do number 4 quite yet. You won't be able to do number 5 quite yet. Neither number 6, neither number 7. Okay, apparently I'm missing. I thought I had a question here dealing with rate law. So what I'm going to do is I'm going to go to Google. Okay, let's see here. Which one shall I choose? Let me see what this has to offer. Okay. I don't want. Okay, what's going on here? Okay. Okay. Oh, this one, they're actually showing you the work. No, that's not as much fun. Let me see here. Oh, okay. Let's see what we have here. What in the world? Okay, let me see what we have here. Okay. Okay, so they're asking for us to calculate the orders. Okay, so this is the reaction right here. This is the data collected. These are the concentrations of NO and Br2. And over here we have the rate, all right? So let me make this larger here. Okay, so let me all right, so basically the rate law would be rate, well, they have it here, but I'm just going to write it in a way that I'm familiar with. Rate is equal to K times concentration of NO raised to the X times the concentration of Br2 raised to the Y. And basically we need to find X, Y, and K, all right? So we're going to use the data values here. I'm just going to label this experiment 1, 2, 3, 4, all right? So for comparing the first two, right? The rate for 1 is 24 m over s, 24, and that is equal to K times the concentration of NO, which is 0.10 raised to the X, M raised to the X, times the concentration of bromine, 0.20 M raised to the Y. And do some similar thing for experiment 2. In this case, it's going to be 150 M over S is equal to K times 0.25 M raised to the X times 0.20 M raised to the Y. And then I divide the top by the bottom. And what do I get? I get the K's canceling out. I get these canceling out. And the M's will cancel out here and here. And these units will cancel out here and here. So I'm going to end up with 24 over 150 is equal to 0.10 over 0.25 raised to the X. All right. So let me see here. So 0.125, whoops, 0.10 divided by 0.25. So this here is equal to 0.4 to the X, and 24 divided by 150 is equal to 0.16. All right. So what is x equal to? How would you solve for x in this case?
2.
Anybody?
It's equal
Okay.
to 2.
Yes, x indeed will be equal to 2. So we're going to put here, whoops, x is equal to 2. All right, so that's the order of the reaction with respect to NO. Now we need to do the same thing for okay, which experiment shall we use? We need to do the same thing for bromine. So let's see here. What experiment? Now, to get bromine, we have to choose 2 sets of data where the concentration of NO is fixed. And based on what I see here, I see that the concentration of NO is fixed for the first and the third, while the concentration of bromine changes, right? Okay, so how are we going to set this up? For 1, it's going to be 24 m over s is equal to k times 0.10 m raised to the x times 0.20 m raised to the y. And then down here, for experiment 3, the rate is equal to 60 m over s, and that is equal to k times 0.10 m raised to the x times 0.50 m raised to the y. And then we divide one line by the other again, like we did before. And of course, the k's will cancel. These will cancel. And of course, the units here will cancel. So we'll be left with, let me just draw a line here to differentiate. There's something going on with my writing tablet here. Okay, so we're going to end up with 24 divided by 60, and that will be equal to 0.20 divided by 0.50 raised to the y. So 24 divided by 60 equals to 0.4, and 0.2 divided by 0.5 would be equal to 0.4, and that is raised to the y. So that means that y would be equal to 1 in this case. All right. So now that we have found the orders with respect to NO and y, we can write down that the rate law, let's scroll down here.
I have a question real quick.
Yes, ma'am.
How did you get x equals 2? I keep getting 2.5. Are we rounding it or?
No. How did you get 2.5?
I'm not sure exactly, like, am I supposed to square root it or to get rid of that
okay.
x or?
Well, you could actually do it by inspection, because I could tell that 0.4 squared is 0.16. But another way of doing it, let me just show you here, is finding the logs of both sides, right? 0.16 is equal to 0.4x, right? Raised to the x. If you find the log of both sides, right? So this is something you should have learned in algebra. You'll see that log of 0.4 raised to the x would be the same thing as x times log of 0.4, right? Which means that x would be equal to log of 0.16 divided by log of 0.4. And if you work that out, you should get x equal to 2.
Okay, thank
Oh,
you. It's
actually-
been a couple years since I've taken algebra, so
0.16 log divided by 0.4 log. Exactly, you get 2.
thank you.
All right. Okay. So let me just put a line here. So therefore, the rate law will be equal to K times concentration of NO raised to the 2 or squared times concentration of bromine. All right. And the third part is asking for you to find K. And if you remember what we did the last time, that would be equal to K, it would be equal to rate divided by concentration of NO squared times concentration of Br2. And all you have to do is put the numbers in. So you could use the numbers from the first set of data. So the numbers from the first set of data would be, the rate would be 24 M over S divided by concentration of NO, which is 0.10 M squared divided by or multiplied by excuse me, 0.10 M raised to the 1, and that would give you the rate constant. So let me do that. 24 divided by 0.1 squared divided by, oh, wait a minute, I made a mistake. It should be 0.2 here. So let me do this again. 24 divided by 0.1 squared divided by 0.2. So the answer I got would be 1.2 times 10 to the 4. And the units, well, this will cancel with that. So the units would be M to the minus 2 seconds to the minus 1. So that would be the answer right there. All right. Okay, any questions about this? Any questions? Okay. Is it okay for me to go away from here right now?
Scroll up really quick.
I'm sorry?
Could you just scroll up a little bit?
We'll scroll up.
Yeah, that's perfect. Thank you.
Let me know when I can leave from that to the PowerPoint.
Okay, I'm ready.
Okay, so let's talk about some specific instances of reactions of specific orders. All right. So let me just skip all this here. Okay, so firstly, I'm going to talk about zero order reactions, right? And in the case of zero order reactions, you're going from your reactant to your product, all right? And because it's zero order, what that means is that the rate of the reaction, which is given by the negative change in concentration of A over change in time, that would be equal to K, the rate constant, times the concentration of A raised to the 0 power. Now, as you all should know, any value that is raised to the 0 power is equal to 1. So what that means is that the rate is equal to a constant, all right? And there are actually reactions where the rate is basically constant. It's not affected by the concentration whatsoever. That might sound a bit weird, but that's basically what happens in some reactions, all right? Now, we can, let me see here. In terms of the units of K, basically the units of K would be basically based on this expression right here. But because the concentration of A is 0, basically unit of K would be M over S. And we can simply put, therefore, this term being equal to K minus the change in concentration of A over the change in time, that would be equal to K. Now, what I'm going to do is show you the result of what we call integrating this equation here. Now, I cannot show you, or I could show you all the steps, but I don't think most of you would understand because I don't think most of you have done any calculus, right? You'd have to have some background in calculus to understand the steps involved. I'm just going to show you the final integrated equation. That's what we call it. And it's this right here, right? So this here leads to this expression. So this expression is basically relating the concentration of the reactant to time for a zero order reaction. So just to show you or indicate what the different terms are, this is the concentration of A at time t, right? This here, concentration of A0, that is the concentration of A at the start of the reaction where time is equal to 0, all right? And of course, K is the rate constant. And basically put them together in this way, you're going to get what is known as the integrated rate law for zero order reactions, all right? So this shows you the relationship between the concentration of A and time for such reactions, all right? Now, at this juncture, I want to introduce to you this concept known as the half-life of a reaction. So the half-life of a reaction is the time required for the concentration of a reactant to decrease to half its initial concentration, all right? Now, this term or this concept of half-life is very important, right? It applies not only to zero order reactions, but it applies to all the other type of reactions that we're going to meet in this chapter, all right? So based on this definition, right, when the time is equal to the half-life, the concentration of A at that time would be equal to half the initial concentration of A. So if you plug in for T here, T half, and if you plug in for A here, this expression right here, which is half the initial concentration of A, then what you find is that this equation will be simplified to give you this equation here. So this is the equation for the half-life of a zero order reaction, all right? Now, what you're looking at here, this graph right here, is basically a plot of the concentration of A versus time, right? So that's the plot of A here versus T. So in other words, hold on, let me get my writing thing out. So in other words, A here would be the Y value, and T here would be the X value, right? So if, again, going back to your math background, you should recognize that this is in the form of Y is equal to minus MX plus C, right? Because A is the Y value, T is the X value, which means that minus M would be the same thing as minus K. And the C here, which is the intercept on the y-axis, would be the same thing as the initial concentration of A. So when you plot concentration of A versus T, as I said before, this is a plot you're going to get, and you can tell what the initial concentration of A is. That's right there. And the slope of this graph would give you the minus K. All right. So basically, if you can plot A versus T, you can determine the rate constant, which would be the negative slope. All right. Okay. So that's basically dealing with zero order reactions. So let me go back to the assignment. Let me go here. Let me see. Okay, so this is the assignment. Oh, let me remove those writings. Okay, so let me scroll down. Oh, wait a minute. I think I went too far. Okay. Number 4 in assignment number 2 says the reaction of reactant A is 0 order, right? So it tells you straight up it's a 0 order reaction. So the first thing that would come to my mind is the equation I just showed you, which I'm going to rewrite here. Okay, so the equation I just showed you is, let me write it here. Concentration of A is equal to concentration of A0 minus KT. And the other equation you might need would be the half-life equation, which is half-life is equal to the concentration of A0 over K, all right? Now, the question says that the initial concentration is 0.545 and the half-life is 236 seconds. So the A part is asking how much time, this is what the question is asking for, it's asking for T is required to reduce the initial concentration of the reactant by 65.5%, all right? So the question is asking for T, right? The question gives you the half-life, the question gives you the initial concentration, and the question is asking for T. So how would we do this? Okay, the first thing I would do is, based on the half-life, since this equation has K here, based on the half-life, I would try to find out what K is, right? So I'm going to rearrange this equation to get K is equal to concentration of A0 over the half-life. So concentration of A0, which is the initial concentration of A, that's 0.545 M, divided by the half-life, which is 236 seconds. So when I do that, the answer I will get is, hold on 1 minute. Okay, so for K, hold on. Did I put the wrong equation? I'm sorry, I think I made a mistake. Let me just check something real quick. Oh, I forgot it too. I know I forgot something. Okay, so let me go back to, okay, so this should be 2 times T half. I apologize for that. So this should be times 2 here. So this should be times 2, all right? So when I did that calculation, the answer I got is 1.15 times 10 to the minus 3 M over S, right? So that's K, okay. So we have the K here, we have the T here, which is what the question is asking for. So basically what we need to do now is determine what A is. And the hint to finding out what A is given right here, the 65.5%. Because the question, notice how the question is worded. The question says, how much time is required to reduce the initial concentration of the reactant by 65.5%? So basically what you're saying is that you're reducing A0, the initial concentration, by 65.5%. So that means that the concentration of A would be equal to 100% or 1 minus 0.655 times the initial concentration of A. Everybody understands what I'm saying here? If 65.5% of A is used up, or if it is reduced by 65.5%, then the amount that is remaining would be 1 minus, or 100% minus 65.5 times the initial concentration of A. So that gives us 0.345 times the initial concentration of A, which is 0.545 M. And when I worked that out, I got 0.188 M. All right. So after doing that, we can now determine what T is. Now remember, this is the relationship that we're working with. We need to solve for T. So therefore, I would rearrange this to get T would be equal to concentration of A0 minus the concentration of A divided by K. And then all I would do is put the numbers in. So the initial concentration of A is 0.545 M minus 0.188 M, which is the concentration of A, divided by K, which we calculated here, which would be 1.15 times 10 to the minus 3 M over S. And then you do your number crunching, which I did, and the answer I got is 310 seconds. And that's basically how that is done. All right. Okay, if you have any questions for this, hold on to the questions until 1 o'clock, and then we'll just continue from there. All right. So we'll take a break right now and then get back together at 1 o'clock.
Wait, the class ends at 1:10 though.
Yeah, no, but
Okay.
I'll still take that break.
All right.
I don't know about you guys, but I need a break. So okay. Okay, I'm back. So I'm just going to quickly go through the next type of reaction, which would be the first order reaction. So let me, before I forget, let me share my screen. Okay, so in the case of first order reactions, okay, what's happening here? Okay. Again, we're going to take the hypothetical example of reactant A forming product, but this time the kinetics are different because the rate now will be equal to the rate constant K times the concentration of A raised to the first power, all right? So that is different from the zero order reaction where this would have been a zero, right? So when we set K equals the rate over the concentration of A, that helps us to determine what the units of K would be, right? The units of K would simply be m to the minus 1, I'm sorry, 1 over S or S to the minus 1, all right? And that's because here we have m over S divided by m as implied by this setup right here, and the resulting unit for K would be S to the minus 1 or 1 over S. Another thing I want to point out is that if we set this expression being equal to Ka, then again, I won't show you all the steps because again, some calculus is involved. The resulting integrated equation will look something like this, right? The concentration of A is equal to the concentration of the initial concentration of A times e to the minus kt. And if you were to plot concentration of A versus T, this is the curve that you're going to end up with, right? So this shows you the relationship between the concentration of A and time for a first order reaction, all right? Another way of expressing this, which is actually more useful, is this expression right here. This expression here is saying the same thing as this. It's just a different way of expressing it, right? This is the natural log of A is equal to the natural log of the initial concentration of A minus KT. And the reason why this is more useful is that if you plot the natural log of A versus T, you're going to get a straight line slope or a straight line sloping line like this, where the slope would be equal to minus the rate constant, minus K, and the y-intercept would be equal to the natural log of the initial concentration of A. So this is actually more useful because you can actually use this to determine the rate constant and the initial concentration of A, all right? So that's basically how the first order integrated reaction works, all right? Now, I'm not sure if we'll have enough time. Let me see what somebody's asking. I'll talk to you about that later, Mr. Lozano. Let me just finish this up right now. Okay, so let me see if I can get to the assignment, see if we can do the zero order. Oh, shoot, you know something? I just realized we didn't get to finish the B part of number 4. My. All right. Let me do this first and then we'll call it a day. All right. Now we're going back to using the same equation, which is, as I said before, right equation here. Concentration of A is equal to concentration of A0 minus KT, right? Now, this question says, how much reactant remains after 6.78 minutes? So what the question is asking for is this, right? So the concentration of A that they're asking for would be equal to the initial concentration of A, which was 0.545, 0.545 m, minus K, which we calculated to be equal to 1.15 times 10 to the minus 3 m over S times over S times 6.78 minutes. However, we have to convert this to seconds. So we're going to have 1 minute here, down here, 60 seconds here to do the conversion. That goes with that, that goes with that. And according to my calculation, when this is done, the answer becomes 0.077 M. And that's how you do that. All right. Okay, I'm going to scratch out this one because this one actually is an impossible question to answer. All right. I think there's a D part. Yes, there is. We can do D very quickly. Any questions about what I've done here, however? Any questions? Any questions? Any questions about what I just did? Going once, going twice? Okay, good. All right, so let me get rid of this and scroll down to the D part. Okay, so the question is asking in D part, at what time will the reaction be over? All right, and it's actually quite simple. The reaction will be over when the concentration of A is 0, right? So if the concentration of A is equal to 0, that means that the concentration of A is equal to 0. That means that this will be equal to the initial concentration of A minus KT, which means that KT will be equal to the concentration of A initially, which means that T will be equal to the concentration of A initially over K. So therefore, that will be equal to 0.545 M divided by 1.15 times 10 to the minus 3 M over S. And according to my calculations, this works out to be equal to 474 seconds. And that's basically how that is done. All right. Okay, so I'm going to stop here for today. Just to answer a couple of questions that have been asked. Somebody was asking about the first exam. That first exam will be on the week of the 14th, which would be, let me see here. Okay, so what I'm going to do is I'm going to send the exam over to the testing center for it to be done between the 10th and the 14th. All right. So you'll have that time period. You can decide which day would be best for you to go there and do the test. Which brings me to another question, not question, but there are a couple of students, I have 3 listed here, who need to do their test at, elsewhere, not here. I have Mr. Watson, I have Mr. Lozano, and I have Miss McConnell. And I think there's one more person that I have been in contact with by Skype, but I don't remember the name of that person. So if you're that person, please let me know where you want the test to be sent to, all right? And if there's anybody else in that situation, please let me know so that I can make the suitable arrangements, all right? Okay, I just saw a question coming up. Is the test just on units 1 and 2? I would say for now, yes. I'm not sure yet, but I'll let you know if the 3rd chapter is going to be included, all right? So I'll let you know about that in due time. So that's basically it. The only other thing I have left for you to tell you is that I have published in Canvas. Let me see if I can bring it up here. Let me see here. Close this. Let me get rid of the writings. Okay, so I've published in Canvas assignment 2, of course. So you can, try to do the questions after watching the videos. Now, the videos, somebody left a message saying that they don't know how to locate the videos. If you scroll down to the module section, where is it? Modules. Where are you? Okay, modules. If you scroll down to the module section, this is where all the videos are located. So what you need to do now is watch the rest of the videos, or watch all the videos for the kinetics chapters, which I published today, right? So these are all the videos. So far, I have gone as far as zero order and first order, right? So you may want to watch all these previous videos as well as the rest of them. And then you can try the questions, but next class, basically at the start, again, I'll do like what I did today. I'll ask you if you have any problems understanding the material, and then we'll move straight into the questions in the assignments, all right? Okay, so that's basically it. If there are no other questions, I will see you guys on Wednesday, all right? Take care.
Wait, so for my testing location, is there a way to find out where the testing location is right now for me?
Okay, who is this?
Watson?
Now, if I'm not mistaken, you said you're at Harrison Air Force Base?
Hanscom.
Hanson, I'm sorry. And this is located where? What city?
Well, technically that is a city, but it's like it's in Massachusetts, near like maybe 40 minutes from Boston.
Is there a college nearby where that base is?
There's like, can it be a community college or?
Yeah, any kind of tertiary institution.
Yeah. Middlesex Community College.
Middlesex, okay. Community college.
Or if that doesn't work, then I can go to any of the ones in Boston.
Okay, all right. Well, let me go with Middlesex for now.
Okay.
All right. Okay, so I'll let you know exactly what the deal is, because I need to contact the folks here to find out. I remember doing this only once, so I don't remember the whole procedure. But I'll contact, the people here and have them guide me as to how I should make arrangements for the test to be sent to that school.
All right. Thank you.
All right. Okay, that's pretty much it for today, folks. So see you guys on Wednesday.
I also
Oh.
had a question
Yes,
about,
ma'am.
so whenever I talked to you about the testing centers, I had given you Texas because I'll be there at the end of the year, like at the time around finals. But for this like coming test, I'm gonna be in Gainesville because I go to UF.
Oh, okay. So this is McConnell. So, okay, so for now it's Gainesville.
Yes.
Okay, but at the end of the term, it's going to be in Texas.
Yes, sir.
And if I'm not mistaken, it's Mansfield, Texas.
Yes, sir.
Okay, so what I'm going to do is make arrangements with the testing center at UF.
Yes, thank you.
All right. Okay. Anybody else? All right. Take care, folks.